Hello, everybody, and welcome to this special evening guest lecture by Dr. Mather. Welcome to Oxford Astrophysics. We are hosting this event this evening as part of a scientific conference about spatially resolved spectroscopy with extremely large telescopes. I'm Niranjan Thatte. I will be your host for this evening. I'm the principal investigator of Harmony, which is going to be one of the first light instruments on the extremely large telescope in Chile, a rendering of which you can see on the background here. It is my immense pleasure today to have Dr. Mather with us to give us this lecture about seeing our history from the Big Bang to now. He's going to tell us about new technologies for new discoveries. After his talk, there will be an opportunity for you to ask questions via the Q&A feature at the bottom of your webinar screen. So if you can type your question into the box that opens up when you press Q&A, then other people can vote on your questions, and we will select the most popular questions for Dr. Mather to answer after his talk is finished. So I have the immense pleasure to introduce Dr. Mather today. He is the senior astrophysicist at the Observational Cosmology Laboratory at Goddard Space Flight Center, where he is currently the senior project scientist for the James Webb Space Telescope. I'm sure you've all heard about it. It's the successor to the Hubble, and it is due now for launch on December the 18th, 2021. So it's an event that all astronomers are looking forward to with great delight. Dr. Mather is very well known. He started his work as an undergraduate and then moved on to do his graduate studies in physics at the University of California at Berkeley. And it's those studies there that inspired the work on the Cosmic Background Explorer satellite. So right after he finished his PhD, he then became a postdoctoral fellow at the Goddard Institute for Space Studies in New York City, where he wrote the proposal or helped write the proposal for COBE, as the satellite was then called. And then he promptly moved to the Goddard Space Flight Center as lead scientist on that mission. COBE was immensely successful. It was the satellite that proved beyond doubt that the cosmic microwave background radiation is a perfect black body down to 50 parts per million. And it was that work that, together with Professor Smoot, then was inspirational for awarding Dr. Mather and Dr. Smoot the Nobel Prize in Physics in 2006. So we are really very fortunate to have Dr. Mather to tell us today both about the James Webb Space Telescope and about some really new ideas for new technology that will blow your minds. So over to you, Dr. Mather.
Well, thank you, Dr. Tate. I'm very happy to have a chance to show you what people are thinking about for these great new ideas for current and future discoveries. I'm going to try to share my screen now and see if I can get those good computer tricks to work properly for you. So here comes. I want to tell you about finding out our history. So it's always seemed to me that this was a fascinating topic, that what we learned in school was probably not right. And probably what we have to tell you today probably still not quite right. But we have a chance to observe it by looking at things that are very far away as we look back in time, as we look out in space. So here on the front page, here is the picture of the great James Webb Space Telescope as it will be in outer space in, well, beginning in December 18th. This is a joint project of NASA with European and Canadian space agencies, and it has taken us a long time. The first conversation I had about it was in October of 1995, so it's almost 26 years now. At any rate, it turned out to be harder than people thought. So new technology had to be invented, and that's part of my story to show you today, is how new technology propels so many great new discoveries. I'm old enough to remember before there was Sputnik, before there was space travel, before there were computers in every pocket. So I am very, very aware of the rapid change of technology, and I can only begin to speculate on how far we will be able to get before we reach some kind of fundamental limits. But at any rate, there is the great telescope. The primary mirror that you see facing you is this great golden hexagon, is 6.5 meters across. It is much larger than the rocket itself, so it will be folded up for launch. It is protected by the sunshade, that gray object that you see beneath it, which is as large as a tennis court, and that will also be folded up to fit inside the rocket. We'll show you the movie later on of how it unfolds after it is launched. So now, however, let me step back to a very great distance from all of these things and talk about the way in which exponential growth has affected our world. In 1965, computer CPU was very elementary compared to what we have now, and it has grown in strength and capability with a doubling time of about 1.5 years for a very long time. So how does that happen? Partly it is that we are able to sell computers of some sort to practically every person on Earth. So there's a huge budget for that to pay all the best engineers and scientists to do it. There's another more generic law about exponential growth of things, Wright's law, which dates back to 1936. It says, if you can keep on building more things, you will gradually learn how to do it better, and it'll get cheaper. So among the other things that have changed rapidly, we keep launching more rockets at a significant growth rate, which compounded over time means many, many more rockets now than before. And now, of course, with the launches of low altitude communication satellites for instant telecommunications with all of our cell phones and the like, it's only increasing rapidly. So even in telescopes, there's been a kind of exponential growth rate for telescope size, and both in space and on the ground. So how far can we continue? That's another question I'm not going to answer. So a long time ago, we thought we were going to collect a single spacecraft with this, after it had done its job, and collect it with a space shuttle, bring it back down, improve it, and send it back up again. That never happened. But now we have already launched 2,000 CubeSats. Now, a CubeSat is based on little modules, about 10 centimeter cubes. You can have a group of them from, say, 3 to 27 little cubes stuck together to build a satellite, and we've got 2,000 of them up now. So you can see there's an exponential growth in that. So now, however, I want to step back, way back in time, to the history of the universe, which I promised to tell you a little bit. Back in 1929, Edwin Hubble drew us this graph. Oops, back up, Mr. Hubble. Here we go. This is a graph showing the velocity of galaxies going away from us as a function of the distance away that he estimated. And so what we see here is every little dot is a galaxy, and almost all of the galaxies are going away from us with a rather great speed. And we see this amazing trend that the farther away they are, the faster they're going. If you divide the distance by the speed, you get the apparent age of the universe. For a long time, we called this Hubble's Law. Now we have decided to call it Hubble-Lemaitre Law, because George Lemaitre, a theorist working with Einstein's equations, predicted that this should occur 2 years before Hubble observed it. So we now should be calling it the Hubble-Lemaitre Law. At any rate, that was the first time in 1929 that we had direct evidence that the universe has an age. Hubble got the wrong answer, not too surprising. He was fooled by his distance measurements. He got 2 billion years for the age of the universe, and now we get about 13.8. Nevertheless, it was started off the study of cosmology as an observational science. So among other things, it was predicted that the universe should be filled with the heat radiation of the early times, whatever that was. If you imagine running the movie backwards of the expanding universe, you say, well, it must have been very hot and very compressed when it was young. There should have been heat, radiation left over from those times. So that was the inspiration for this observatory, which was Dr. Thate mentioned to you. This was the successor for my failed graduate student project. We tried using a balloon payload in Berkeley to measure the cosmic microwave background spectrum to see if it didn't match or not with the prediction. And so it failed to work, but I knew what I wanted to do next, and I got a chance when I moved from Berkeley to my first job at the NASA laboratory in New York City. At any rate, we proposed this. 15 years later, it was launched into space, and it worked because real engineers made it work. This project earned us a Nobel Prize, and I like to remind people that it took 1,500 people to build that little observatory. Things have gotten a little easier now. We could do the same thing now with much less effort because the technological infrastructure has improved dramatically. When I started at NASA, we drew observatories on big pieces of paper with sharp pencils. Now we don't use pencils anymore. We use computers. So at any rate, this was launched. It was followed soon after by the Wilkinson Microwave Anisotropy Probe in 2001 and the Planck mission from ESA, and many, many, many ground-based instruments have confirmed the story. But at any rate, here is our spectrum showing the effectively perfect agreement between the prediction of the Big Bang or expanding universe story and the measurements that we got. So can't escape. Although there were some very creative people who wished to escape the story of the expanding universe. At any rate, now, of course, we have to continue to explore this. The question at stake today is, well, what about the spots? The cosmic microwave radiation from the early universe should have spots, does have spots that represent density variations in the early times. And so we have been building equipment in space and now on the ground to measure that better and better and better. One of the things you can measure is to look for the polarization of that radiation, which tells us something about the possibility of gravitational waves in the very, very earliest moments of the expanding universe. So there's one. It's in the desert, in Atacama Desert in Chile. We also send equipment down to the South Pole, and here are two pieces of observational equipment to look at that microwave background radiation. It's a hard life if you want to do this, and it takes exquisite engineering, which is why I think it's worth concentrating a little bit on the technology behind all the great discoveries that we have. So I don't have time to tell you the details about how it works, but I just want to show you that it takes tremendous ambition and tremendous creativity to be able to even imagine building such a thing at the South Pole. And then it requires huge logistics support because you cannot just drop in. So, as you know, the Hubble Telescope has been up there for a long time. It's hard to imagine that it is already 31 years old and it is still working beautifully. Of course, why is it working well? Well, two things. One is we've sent our astronauts up 5 times to improve it and repair it. And number two is it has 2 of everything where it's possible to have 2 sets of electronics. So recently it had a failure in the springtime, and we had to shut it down for a while and decide exactly how were we going to switch over to the redundant backup electronics. And after they thought about it for about a month, they tried it and it worked. So the Hubble Telescope is back up and still running and still doing things that were thought to be completely impossible when we started. So here's an example of one of its most important famous discoveries, and it's totally relevant to the conference of today because the Hubble measured a mass of a black hole in the M84 Galaxy. So what's shown here on the left is that they put the slit of the spectrometer right across the center of the galaxy in question, M84. On the right-hand side is the spectrum. And you see that it goes, has a change of color, which means a change of wavelength. It means on the left-hand side, which is to say just a little bit above the nucleus of the galaxy, the light is blue shifted, so objects are coming toward us. On the right-hand side and below, they're red shifted and going down. So from the velocity change that's implied by this picture, we can calculate the mass of the black hole in the middle. So it's a first very direct observation of the mass of a supermassive black hole. requiring spatially resolved spectroscopy. And now, of course, we want to do it all more and better. So other things that we do. We have built an observatory in South America in the desert, way up at 5,000 meters elevation, which is practically unsafe for ordinary people to go because there's not enough air. At any rate, this is a computer-controlled, computer-generated telescope combining about 60 little antennas that are connected by fiber optics and digital correlators and computers that are used to draw pictures like the one on the left, where it says dark dust, that we're observing dust grains orbiting around a brand new star. This is the first observatory that was able to get us such a beautiful picture like that. It's thought that there are about 9 planets growing in that nebula around that new star. And if you were to come back in 100,000 years, maybe the dust would be gone and the planets would still be there. So astronomers need a little patience. We want to see what's going to happen. So another totally astonishing technology for me is the Event Horizon Telescope. This is another synthetic aperture, a computer-generated telescope where they combined signals that were observed in 10 different locations at the same time. They recorded these signals on computer hard drives, and they drove them or flew them to a combining station in the United States, and the computers said, this is what it means. And they were able to draw us a picture of a black hole and the shadow that it casts there on the left. And it has been astonishingly powerful, and it could be improved, of course, as our colleagues on this team tell us, that we really need to add a space telescope orbiting around the Earth to observe this picture much more quickly. Because sometimes the black holes change quickly, and you have to make the measurements before they change. Not impossible, and it's something that required as much ingenuity as it required equipment. Most of the equipment was already in place when we wanted to do this project, but then we had to figure out a special and new way to record all that information and combine it in a computer. So here's the opposite extreme. This very, very, very small observatory was composed of 24 fairly ordinary but very nice camera lenses. These are things you can buy yourself. They said if we get the very best digital camera equipment to go at the back end of these camera lenses, we will be able to hunt for dark matter. And so here is one of their observations. They covered a huge amount of sky with this little camera, or a set of cameras, and they found an object that, at least at the time, seemed to be 99.99% dark matter. How would you know that? Well, you go take a picture with a better telescope, a bigger telescope, and you see, does it move? You need spatially resolved spectroscopy to tell whether those stars in that little galaxy are zooming around very quickly, as they would be if there's a lot of gravity to hold them together. But the little thing is so extremely faint that you say, well, there are hardly any stars in there. It's almost all dark matter. So a very, very small telescope can also make a wonderful and challenging discovery. So here is a story about one of our most startling discoveries, that gravitational waves can be detected from black holes combining with other black holes or with neutron stars at immense cosmological distances. This is the LIGO, the Laser Interferometer Gravitational Wave Observatory. It's now an international project with pieces in the United States, in Europe, and coming along in India, I think, and maybe even Japan. At any rate, the object of this observatory is to see these little mirrors on the sketch in the bottom tremble ever so slightly when a gravitational wave comes by. And they do. But the amount that they move is extremely small. It's much smaller than the size of the atomic nucleus. So huge technological accomplishment, and of course was rewarded by Nobel Prize for 3 of the leaders of that project. Again, like all of our great projects, it takes a lot of people to do something. So here's another thing that's coming along about gravitational waves. Jocelyn Bell discovered a very long time ago as a graduate student that there are pulsars in space. We now think that they are spinning magnetized neutron stars, and they spin around up to 1,000 times a second. They are extremely good clocks. Nothing bothers them very much. And so they are so good that you can use them to tell whether gravitational waves are coming by. It is getting pretty close to where they say we should be able to detect actual individual objects that are sending us gravitational waves at very low frequencies. Where I say very low, this means waves per year. That's what we mean by very low frequencies. So we will learn, we will find out. Another thing we're working on that is actually perhaps hopeless, but we don't know. We have all heard about dark matter and dark energy. This is an apparatus that was invented and built in order to hunt for dark matter in case it is made out of axions. So what are axions? It's a hypothetical quantum mechanical field that you can describe if you imagine what it should look like. If that has a particular mass, the particles in this particular field, and you add a magnetic field to that object, then perhaps we'll get a microwave photon. Well, they tried. They tried very hard, but there was nothing there yet. So the answer is all of our experiments to look for dark matter in a laboratory have failed. That doesn't mean there's no dark matter. It just means that it is so dark, which is to say so non-interactive, that nothing we can imagine yet has found it. We are quite sure as astronomers that it is there. It has all of the right properties to be to explain the orbits and motions of particles in our galaxies, but we can't see it here on Earth. So what else is coming? Well, we have recently launched a little satellite with 4 big fat camera lenses to look at the sky from space. And the purpose of this one was to look for stars that blink when a planet goes in front of them. And so if you watch long enough, well enough, you can find a lot of them. So they've been watching about 200,000 target stars and have found over 2,000 candidates for being planets around those stars. Over 200 of them are confirmed as planets, meaning we've been able to verify that they have just the right properties to do what we say. That is to say, they blink in a regular fashion, they have plausible properties, and perhaps we have even some other evidence that they're really there. So here's the great Webb telescope I was telling you about at the beginning. It's a summary of what it is and who does it. It is being led by us at NASA Goddard Space Flight Center. We are located just outside Washington, D.C., in suburban Maryland. And our partnership is with Europe and Canada. We have one very large aerospace contractor we're working with, Northrop Grumman Aerospace Systems. We have 4 instruments behind the telescope that come from all of our partners. One from the United States, that's a near-infrared camera. One from Europe, that's the near-infrared spectrograph. One that studies the mid-infrared wavelength range, that's a partnership between Jet Propulsion Lab and Europe. And finally, there's the fine guidance sensor and a special spectrograph that comes from Canada. So like the Hubble telescope, this will be operated from Baltimore at the Space Telescope Science Institute. If you've been finding beautiful pictures and data releases from the Hubble telescope, then you go to the same place as you did before. So the telescope there, as shown, is 6.5 meters in diameter. It will be operated at very low temperature, at about 50 degrees Kelvin, 40 degrees Kelvin, so that it does not emit much infrared. And it is going up on the European rocket, the Ariane 5, on December 18th. That's the plan. We are carrying fuel, which we need to keep it going for a period of 10 years at least. And if we're fortunate, it might last for much longer than that. There are 4 main themes that we identified very early on for the scientific observations we wanted to make. What is the first thing that happened after the Big Bang, the first galaxies and stars and black holes that grew? How did the galaxies grow from there? How are stars born today? And what about planets? So all of those things are being planned for observations in the Webb Telescope program coming up. So how good is it? Well, if you were a small insect, 1 square centimeter in space at about the temperature that you would have if you were there, we would be able to see you both by reflected sunlight that a small insect would have, or by the heat that the object would re-radiate. But please sit there for a long time because it takes a time exposure to do this. An interesting challenge was the opposite, to look at really bright objects here in the solar system. Mars is the brightest one we would look at, and we have a way to do it, but we can't just take a picture. We have to take a picture of a very small portion of Mars and then spread out the light with spectroscopy, just as the subject of our conference, so that we can actually catch the photons and read them before the detector is full up. So we will be able to observe moving objects in the solar system all the way from Mars on outwards, and we can even look at what's called transit spectroscopy of everything except the very brightest stars. Oops. So examples of what we're going to look at. This is a piece of the Hubble Space Telescope deep exposure we did called the Hubble Deep Field. Astronomers decided to point the telescope at an empty place in the sky where there was one star and a few others. And they found, to their amazement, that there were thousands and thousands of galaxies in that very small region. And they also found, to their surprise, that galaxies had grown very quickly after the Big Bang, and we were not able to see the first ones growing. The telescope was too small because objects are too far away and faint, and the telescope is too warm. In other words, the Hubble telescope glows and emits at infrared wavelengths that we would need to use to see the most distant objects. And that's because the expanding universe stretches out the light from the most distant objects and makes ultraviolet turn into infrared when we receive it. So astronomers looked at this beautiful picture. They said, "It's beautiful. Please build us another more powerful telescope." And that's what the James Webb is. What else will we look at? Well, this is an example of showing how you can see inside dust clouds by looking at longer wavelengths. On the left side, you see the visible picture that we have. Dust clouds in space are opaque. You cannot see inside where stars are being born. On the right side, we show the infrared capability of the Hubble. And you can see a lot more stars. The dust is much less opaque. But you can see it still blocks the visibility to the innermost parts where stars are being born right now. So definitely infrared will be powerful, and it's a way to find out about the birth of stars. We will be looking at things in the solar system. I think everyone is aware that we are hoping and planning to send missions back to the outer solar system to places that have geology and possibly who knows what life. On the left side, we show the picture of Europa, which is a satellite of Jupiter, which is known from a NASA mission called Galileo that took pictures and told us that Europa is covered with ice, that there's a liquid ocean under it, probably salty. And now we know that once in a while, water comes out, liquid water comes out from the cracks between the pieces of ice. So now we are planning to send a mission called Europa Clipper that will fly through those plumes of water vapor to see if there are organic molecules in there. Long time ago, when we first knew that the satellite had a liquid ocean, we said, we need to send a nuclear reactor to melt our way through so we can see what's in that ocean. We don't have to start there. We can actually go and collect samples of the water as it's coming out. Or a little more ambitious, we could land on the surface and collect water in great abundance, do a chemical analysis. On the right-hand side, we have a geological map of the surface of Titan. Titan is the largest satellite in the solar system. It is cold. It's so cold that it can have a good thick atmosphere, mostly nitrogen, and it has rain. It has liquid rain of hydrocarbons, methane and ethane, for instance. And it has They're for a geological surface. What we think of as rocks are made of solid water ice on Titan. We are planning a helicopter to go fly around a little bit on Titan to examine the surface and think about what to do next. This is a remarkable place if you think that life doesn't have to be like life here. In particular, if you think water isn't the only solvent that could support living material, then why don't we look at a cryogenic situation where the solvent is liquid hydrocarbons and there's abundant carbon and other materials to try complicated life. So we don't know quite what to look for, but we certainly are going to look. With the Webb telescope, we will also be looking at other planets. I mentioned that when a planet goes in front of its star, the star can blink. We have the capability of analyzing the light that goes through the atmosphere of the planet on its way to our telescope. So we measure the spectrum of the star before and after the presence of the planet blocking the light, and the difference shows us what was due to the planet, and then in particular what was due to the atmosphere of the planet. So we think we should be able to look for some molecules, and in particular water molecules in the atmospheres of little planets around other stars. And we have a pretty big catalog of places to look. And they're already definitely part of our observing program for the first year. So 9 little ones, size of Earth about, 5 bigger ones about the size of Neptune, and some 16 Jupiter-sized planets. And nobody's expecting those Jupiter-sized planets to be like Earth, but they sure are a lot easier to see. So just a little bit about how do we get the Webb telescope built and up into space. So here I'm going to show you the steps along the way. First, we put the telescope together in our clean room at Goddard Space Flight Center. There it is, folded up in gold. At this point, we had already completely assembled the instrument package, which has the cameras and spectrometers that are hidden behind the telescope. After it was put together, we put it in a clean tent, and we carried it over to a shaking machine where we were able to apply 50,000 pounds of vibration force to see if it would break. Of course, we don't want it to break. We learned that it would survive launch if we treated it well. And so after we survived the test, we put it in a shipping container and sent it by aircraft, including the whole truck, around to Johnson Space Center in Houston, where you think astronauts come from. They did actually have a gigantic vacuum chamber there that the astronauts used to prepare to land on the moon. And they walked down their little ladder from the Apollo space capsule. At any rate, we had to improve the chamber so it would get cold enough to simulate having our telescope in outer space. So after it survived that test, including the human beings surviving a hurricane where well over 1 meter of rain fell on the outside of the building, we put it back in the shipping container and the airplane, sent it off to California, and connected up the telescope part with the warm part of the observatory. We made sure that it would unfold and fold up properly. And now we're buttoning it up and getting it ready for this trip. It is going by boat from Southern California through the Panama Canal all the way to the launch site in French Guiana. So why do we go to French Guiana? Well, that's because that's where the Ariane 5 rockets go. It is a part of France, and it's been launching rockets there for a very long time. This is one of the most reliable commercial rockets, and we're pleased to be able to go on it. And we have only one other launch in front of us, and so now we're able to say what the schedule is, December 18th. So then we push the button, or someone pushes the button. The observatory will fly all the way directly to the distant location called Lagrange Point 2, and it will unfold on its way out there. So that's so what's supposed to happen, and it will take altogether 6 months after launch before it is fully set up and ready to go to do astronomy. So in June of 2022, we should see many beautiful pictures beginning to come out. So this is where we're going. This drawing is not to scale exactly, but it shows the sun, the earth, and the moon there. And if you go from the sun to the earth another 1.5 million kilometers farther out from the sun, you get to the Lagrange Point 2. This is a place where the combined gravitational force of the sun and the earth are just enough to pull the observatory around the sun once a year. So we can stay there, but it's a little bit unstable as an orbit, so we do occasionally have to fire the rocket jets to stay there. Here is our movie that describes what's going to happen. This takes about 2 weeks to accomplish all of this unfolding. First, of course, we unfold the solar panels because we want to make sure the battery never goes empty. We unfold a transmitter and receiver antenna so we can talk better to the observatory. We unfold the sunshade itself, or the covers that hold it. We separate the telescope from the warm part of the observatory. We unroll the covers. Then we extend the booms to stretch out the sunshade. We pull on some cords and separate the layers of the sunshade. Now, there are 5 layers because we really have to make sure that telescope gets cold. And you can see that it's extremely complex. The only way we would ever dare to build a thing like this is that the companies that we work with have done extremely complicated things in outer space before. Still, this is the very first time for this one. And so we have had an extremely long test program, very cautious review boards who were, as we require them to do, they tell us when we're wrong. That's the only way you can possibly get something like this to work. And by the way, just as on the Hubble Telescope, we have 2 of everything electronic where it's possible. So this is where you can follow us on the internet as we get ready to launch and after we launch. If, of course, you find all these things by Google, a search on the internet will turn them all up. We have gone to great lengths to document what we can do for professional astronomers and to provide guidance. In fact, we especially had to provide guidance because we held a competition to decide what would we look at. So the competition was open to astronomers around the world, and we received over 1,100 proposals, and we chose them anonymously in the sense that we just read them very carefully without knowing who wrote them. And Europeans should be proud to say that they were selected to lead over 30% of the observing programs. And graduate students should be proud to say that they were chosen for 10% of the observing programs. So we are now getting to where graduate students' initiative and creativity can be recognized by NASA. So I just want to go a little beyond this to say what is going to happen next after the Webb telescope, because this is certainly not the last telescope. We have some that are already under construction and are about to be launched, and many more that we would like to build someday. So probably the next one you might know about is the Euclid mission. It's planned for launch by European Space Agency. It has some partnership from NASA and the Jet Propulsion Lab. And the purpose of it is to look for dark matter, dark energy signs. And it has a relatively small telescope, which means it can be done sooner than more ambitious ones. And it's going soon, within a year about. We have an American one. It's twice as big and is taking another 4 years longer to get ready to go. It has, in addition to the similar kinds of observations, it's also the ambition to observe exoplanets. Would be the first big observatory in space specially designed for exoplanets. And what makes it special is we're working very hard to be able to hide the star and be able to find the very faint planets next to it. So how hard is this? Just to give you some perspective, the sun is 10,000 million times brighter than the Earth. So it's extremely hard to find an Earth next to a sun. So that's just a tough job. So you really need extremely good optical system to do it. What else is coming? Well, of course, on the ground, our fellows are building the biggest possible telescopes as well. This one is being completed now. When it starts, it will be totally astonishing. It has an 8-meter diameter mirror, 3.2 gigapixel camera, and it will take a picture of the entire sky from its perspective every 3 days. So the point of it is to see things that change, as well as to survey the sky. And they expect to tell us every day 10 million things that changed. So there are not 10 million graduate students, so we're going to have to get computers to help to figure out what does that mean. By the way, this is also one of the telescopes that's extremely susceptible to interference from the mega constellations of communication satellites that are now being launched, because this camera takes a picture of so much of the sky that a large fraction of the pictures will have streaks from satellites going across. We will figure it out. We will cope with it, but it's an unexpected challenge. What happens next? Well, there are actually 3 different totally gigantic telescopes being prepared today. The European one is the only one that is fully funded and fully under construction. But in something like, I don't know, 2027, we hope to have it looking like this as shown in the upper right corner. It's hard to imagine how big that is. The aperture is about 6 times the aperture of the Webb telescope, which is to say it collects 36 times as much light. It also works at shorter wavelengths, the visible wavelengths, to see things that even the Webb telescope cannot see. So, but we need a special trick. We need to be able to focus on something in space through the turbulent atmosphere of the Earth. And so we've been able, in principle, to do this, to know what to do since 1953. And now we are doing it. And it's a very challenging thing. The current method is to send up laser beams from the ground and to make little fluorescent spots in the upper atmosphere, and to use those to help us focus the telescope as though there were no longer an atmosphere fluctuating overhead. An alternate technology that we've been exploring at NASA and is also being explored in Italy and in Canada is to fly a satellite beacon beaming a laser down to the Earth from above. So we think that's another way that's a very powerful one, and one of the days we should have both working. I show the right-hand side picture to emphasize that it is also once in a while possible to get a remarkable benefit for general society from astronomers' work. On the right-hand side, you see adaptive optics used in a very similar configuration. When your eye doctor wants to see the back of your eye, he or she has to look through the imperfect eyeball that you have. And you say, well, isn't that sort of obvious? Of course, that's what you would want to do. The special story to tell you is that the engineer who figured out how to measure the Webb telescope mirrors as we were building them is the same person who designed the system that you now can get in every doctor's office, every eye doctor's office. So it's not that the technology was transferred, but that the person who invented this one had the basis for a knowledge for doing it. So here's an illustration of the idea of the orbiting guide star. Just a little laser beam coming down from above, shining on the telescope on the ground. On the left-hand side, you see the Keck Observatory, which is currently the largest one in the world, shining its laser beam up to cause a fluorescence in the upper atmosphere. So this is not impossible, and I think it may end up being a method that every observatory will want to use when we get it going. If you could get it going, you could do the next step, which is to fly a star shade. A star shade can be put in space to cast a shadow of a star onto the telescope without blocking the light of the planets. So this illustrates how that might be done. We put the star shade, in this case, in a very long elliptical orbit around the Earth. We have a telescope on the ground, like the EELT. And we calculate that if we could do this and match the orbit for a while, then we would be able to take a picture of a solar system in a minute, as shown in the right-hand side. Earth, Venus, and Mars would show up very well in a minute. And if we try a little harder, we can even get a spectrum. So what we need is the spatially resolved spectrum of a solar system way out there. And here are pieces of a synthetic spectrum, showing you a number of curves. The blue one in the lower panel is a hypothetical Earth way out there, showing that such an Earth would absorb light at certain wavelengths due to oxygen and water in its atmosphere. And we would be able to tell here on Earth, even though we have to look through our own atmosphere, which has its own oxygen and water to interfere with our measurements. We would be able to see hypothetical Jupiters and Neptunes if they were a little closer to their star. They would be very interesting objects too, and they're of course much easier to see. So these are all not impossible. I would not say that they are possible, but they are not impossible. So coming after that, we certainly have already got a plan to build this observatory. It's called the Laser Interferometer Space Antenna. It's a space version of the ground version, the LIGO observatory that earned its Nobel Prize for measuring black hole mergers. It is an astonishing concept. It's been under discussion for over 40 years, and it's not impossible, and we are doing that one too. What happens after this? I do not know. NASA works with a committee of the National Academy of Sciences in the United States to ask for a priority report. So they are just in the business of finishing it up. Within weeks, we expect to see the answer to which of these observatories that are shown here might be the chosen one to build next. So on the picture, they are showing you two versions of ultraviolet, visible, and near-infrared telescopes that would be really good at seeing planets. There's also an X-ray observatory called LINX, and there's a very far infrared observatory called Origins Space Telescope. So which will happen, I do not know. The committee's report is extremely secret until it is released. So coming soon, you should expect to see news about what this committee recommends, and of course, NASA likes to do what the committee says. So wish us luck. There are many possibilities of additional projects after this, but I think I'm running out of time, so why don't we stop and take some questions? And say that we naturally don't know the answer, but we'll have questions. Let's do questions. Thanks, everyone, and I'm eager to have your questions.
Fantastic. Thank you very much, John, for a really fabulous talk. And it's really mind-boggling, some of the technology that we have built over the years. Right, so questions, there are many. I think I'd like to start with a couple about the James Webb Telescope. One is asking what mechanism is used to cool the James Webb?
Okay, well, how would a telescope get cold in outer space? Well, outer space is cold if you're not looking at the sun. So the telescope will cool itself down to about 45 Kelvin just by radiating its own heat directly to space behind its umbrella. But we also need a special refrigerator because one of the instruments has to run at 7 degrees Kelvin. So it uses a helium refrigerator. Helium is compressed with the pumps on the warm end of the observatory, and that passes through very thin tubes and expands at the cold place and cools that instrument. So this is the way that we keep that one going. It's not supposed to ever stop. Unlike stored cryogen, it should run forever.
Okay, wonderful. Thank you for that. And somebody else is asking, if you flew the James Webb across the United States, why couldn't you fly it all the way to Kourou? Why did it have to go on a ship?
Oh, yes. It's a funny thing. There is an airstrip in Kourou, but there are 7 bridges between the airstrip and the rocket launch spot, and they're not strong enough to hold up the payload. So we thought, well, why don't we just take the boat instead of having to build 7 bridges over again?
Very good. So here's a really challenging question that is asking, what would be the greatest discovery you'd like to see in your lifetime? And what would you like to say to a teenager that is thinking of studying science or astrophysics or space exploration? What would be their greatest challenge?
Oh my goodness. Well, there's a wonderful question. I would love to be surprised by something that's out there that nobody has yet imagined. Astronomy has historically been an observational science where the most important things that we find are the ones that nobody ever thought of before. So I showed you already the measurement that Hubble took with a black hole in the middle of a galaxy. We guessed. We imagined maybe they were there, but somebody said, that's the place to look. And they saw that there is one. Now we think all galaxies have black holes in the middle. I'm thinking we have opportunity for big surprises in 2 obvious areas. One is in the very early universe, where we really haven't seen much to be able to help our imagination. So what if, as an example, there was another category of objects that was maybe made out of some different kind of particle, dark matter particle, something where all of the examples of this kind of object, they were all formed and they all burned out completely, so there's none left to find in today's universe. So that's one kind of surprise we might hope to find. The other territory that seems to me ripe for surprise is in the study of planets. Almost everything we know about planets was a surprise. First, we thought planet must be rare because the solar system seems special to us and nobody could imagine how planets would grow. Then we were shocked to discover that most stars have planets, and most stars have small planets, and about 20% of them have small planets that might be like Earth. So this was all a huge surprise. Well, what else is out there? Now we even know that there are about as many loose planets orbiting in space without any star as there are planets that have stars. So that's pretty shocking. And a few of them can be discovered indirectly. So I think we're going to learn a lot more about planets that will surprise everyone.
Thank you very much for that really informed answer. I think certainly the next generation of telescopes, both on the ground and in space, is going to transform the way we do astronomy. And I think for teenagers in particular, it will be a very different astronomy to the kind that we have done in our lifetimes. There are lots more questions coming in. If you would like to field a few more. One is asking a bit more about the James Webb Telescope. Can we use the JWST to get an image at higher resolution of a black hole? And would that be of particular value to scientists?
Yes, a little bit. The images that we get will be a little sharper than we can get with Hubble. And the infrared capability means that we can see farther into the nucleus of a galaxy. A great many black holes have dust clouds around them. So, however, it's really not the best tool. The best tool is going to be something like the Event Horizon Telescope.
Indeed. And I think there's a related question about the Event Horizon Telescope, which asks you to explain a little bit more about synthesis imaging, in the sense that it's asking, why do multiple telescopes help if they're all about the same distance from the black hole? Why do multiple telescopes give us a sharper picture than a single telescope would?
Okay. Multiple telescopes help us because light is a wave, at least for this purpose. Because light is wavy, it means it gives us a fuzzy picture if the telescope is not large enough. So the aperture synthesis with the computer lets us pretend and simulate having a telescope that's almost as large as the Earth. So that's why we need the Event Horizon Telescope to get that particular kind of special image. It's a way of simulating a very, very large telescope and getting a much sharper image. So with micro arcsecond resolution instead of milliarcseconds or seconds, the way that we can see with ordinary equipment.
Okay, thank you for that. You talked about finding Earth 2.0 as one of the standout discoveries that we would like to see in our lifetime. Somebody's asking whether it makes sense to look for planetary systems where there is a Jupiter or Saturn-like outer planet in order to deflect asteroids or protect the potential Earth-like planet from bombardment by asteroids.
Yes, I think it's a great idea. Unfortunately, it's pretty hard to work on because the equipment that we have is probably not capable of seeing those Jupiters yet. So for the next generation of observing programs, maybe with the WFIRST, the Roman Space Telescope, we'll be able to see a few. We don't know what will limit its capabilities, but I'm sure that there is ambition to do just exactly what your question said.
Okay, and then still sticking with exoplanets, can you explain a little bit more about how the star shade could be moved around to change its position when we look at different stars? And would you need to change its size to adapt to different star sizes or different luminosities?
Yeah, good question. So for every different target star, we need a different place to put the star shade. So yes, indeed, we need a lot of rocket propulsion to move it from place to place. We didn't go into details, but we would use solar electric propulsion. So we receive solar energy, use it to accelerate ions to extremely high velocities to get enough force to move, but rather slowly from target to target. I didn't talk about it, but we also have to apply rather much larger forces to keep aligned during the observation, because the Earth is spinning the observatory around quite rapidly, and that's accelerating. So we have to match the acceleration of the observatory while we're looking. But no, we don't really think we have to change the shape of the star shade. It's a hard problem, which will be for a next generation.
Okay, thank you very much. And then something about the future of JWST. Do you think it will be possible to refuel or repair James Webb like we have done with HST when it is eventually required?
Good question. We did not design it for that because when we started, it was hopeless. There are a few things we could imagine doing. Yes, in principle, we have access to the fuel tanks, so we could put in more fuel. But I would say, observing what my fellow astronomers like to do, they will say in 20 or so many years, whenever the fuel is gone, oh, that was great, we need another better telescope.
Indeed, maybe
so
the
we
decadal
do that
survey.
all the time. Please build us a better one.
I was going to say maybe the decadal survey in a few years to come will recommend exactly that.
Yeah, we'll see what they do.
Okay, you talked a little bit about the redundancy that was built into Hubble, and you told us that also on James Webb, all of the electronics that can be made redundant has been made redundant to give it that extra boost in terms of lifetime. Is it particularly problematic for James Webb because it's much further away from Earth, outside of the Van Allen belts, and is much more susceptible to charged particles, radiation? Is it harder to keep it from environmental problems of those kinds?
Well, good question. Of course, it's a little harder, but we also know what the environment is. So when we say all the parts should be tolerant of that amount of radiation, then of course we think that they are. One thing that's interesting and different is that Hubble and Chandra use CCD detectors, charge-coupled device detectors, and they are quite susceptible to damage by cosmic ray bombardment, and Webb Telescope uses a different kind. So those detectors are not nearly as affected by cosmic rays.
Indeed. Okay, so thank you very much for your patience in answering all these questions. I think I will take two more. The penultimate one says, we know very little about dark matter. And do you think astronomy will be able to exploit it more in the future? But I think they mean, do you think we will be able to know more about it in the future? You spoke about that in your talk.
Yes, I do think we'll be able to learn more about what it does. We have currently a description that says it's cold, and that's good enough. Cold means it doesn't move very fast. There is a large number of people who think there could also be a warm dark matter that moves a little faster. And we should eventually be able to make astronomical tests to tell us the difference. So that will be a matter of interpreting how the gravity works, because the only way that we know now to tell is because this dark matter has gravity. So, and of course, there's always the competing theory that says it's not really dark matter anyway, it's just a fault in our theory of gravity. But I don't know how to take that one.
Indeed, yes, modified gravity theories. Okay, so the final one is actually about gravity waves, and I'll probably try and combine two questions that are on my screen here. One says, would gravity waves affect the Earth in any way? And the other asks whether the ones we have detected, are they just a single blip or are they a series of blips?
Okay, well, in principle, to answer the first part, every wave that comes by affects the Earth, but these waves are so weak that we would never know unless we tried with special equipment. So probably there's something happening all the time that no one could ever measure. About is it a series or just once? What we see currently is an event that lasts for a fraction of a second, where the waves are strong enough for us to see. But we calculate that, of course, waves are coming for many, many years before we're able to see them. So as an example, the first demonstration that there must be gravity waves was by watching their effect on binary pulsar. And we saw that the binary pulsar was losing energy, and the assumption was, well, it must be losing energy by radiating gravity waves away. So that does that over millions or billions of years. Very, very long, almost sinusoidal wave. But they only get bright enough and fast enough for us to see in a very short time so far.
Okay, thank you very much for your patience and for taking the time to give us this excellent talk and tell us about all the latest, greatest in terms of technology and science that is coming our way in the coming years. It was a real pleasure to host you this evening. We hope it could be in person, perhaps at some point in the future when COVID-19 allows. We would very much like to welcome you to Oxford. In the meantime, for the audience, if you would like to follow this talk later on YouTube, please subscribe to the Oxford Physics YouTube channel, and Dr. Mather has kindly agreed for the talk to be put up there, so you will be able to review it and go through some of the more intricate points at your leisure. So thank you everybody for attending, and it was a great pleasure once again, Dr. Mather, our most sincere gratitude. Thank you very much.
Well, thank you for arranging it. I've enjoyed talking with you. All the best.
Goodbye, everybody.